Okay, so I think we can start. So today I am going to talk about X-ray astronomy, and we have two lectures on X-ray astronomy. And I suppose you are from our masters, BTech. So I'll try to cover from the very basics. And you can actually, if you have a question, you can stop me and ask. There is no problem with anything you are not able to understand. We'll need to ask. Okay. So we will walk through the basic questions. For example, what are X-rays? Many of you would already know, but for the sake of completeness, I'll cover these things. What are their properties? How are X-rays produced, particularly in the astronomical context? And how do X-rays interact with the method? These are some of the important questions to know about the basics of X-ray astronomy. So as you know, the X-rays were discovered by Ronson, W.C. Ronson in 1985. And he discovered quite by an accident when he was experimenting with electric discharge in gases. So what he did, he used electrodes, essentially the gas discharge tubes filled with some gas, and he applied high voltage onto the cathode. So what that happens when the cathode is the electrons, and the electrons interact with whatever gas is there, and that interaction produces X-rays, which was observed by Ronson in the 10th globe. And these radiations were not unknown at that point of time, so he named these rays as X-rays, and that is how he discovered X-rays. And this is the first X-ray image, an X-ray picture of a human body. This is the X-ray image of the hand of Ronson's wife statue. Okay, so this is Ronson's statue. And here, from the very basic, this X-ray image, we can infer some of the properties. First of all, you see there are very dark regions. The ring here in this figure is very, very dark. So what it means is that all the X-rays which are trying to pass through this ring, which is I think the gold ring, are stopped by the gold. Okay, but look at the bones here. You can see the bones here. The bones essentially contain calcium. The calcium is also stopped, but not effectively as gold. Then the other parts of the hands, which has the carbon, oxygen in the flash, those are essentially transparent to X-rays. So what it means is that the X-rays pass through very easily through lighter elements with low atomic number. So for example, carbon has Z equal to 6, atomic number equal to 6. Oxygen has atomic number 8. So the X-rays generally pass through carbon, oxygen. And while X-rays are stopped by heavier elements like calcium, which is atomic number 20, and gold, of course, atomic number 75. So this is one of the very basic properties just inferred from the first X-ray image of Ronson's wife. Okay. So what are X-rays? X-rays, of course, are the electromagnetic radiation, like the visible light. Okay, but their energy, the energies of these X-ray photons are 1,000 times more compared to the energy of the X-ray photons. That's the difference. We have to remember that the X-rays are 1,000 times more energetic compared to the visible light photons. What is the X-ray band? You know what is the band? What is the visible band? What is the range in wavelength for the visible band? Sorry? 400 to 700 or 800 nanometers. That is the visible band. But X-rays, if you see, the X-ray band starts from about 1 angstrom, then it goes to 100 angstrom or so. Okay, so 1 angstrom, when you say, it's like 100 kilo electron volts. And when you say 100 angstrom or 10 nanometer, it's a fraction of a kilo electron. So it is from the X-rays, and X-ray band is defined by the fraction, generally taken is from a fraction of kilo electron volts to several hundred kilo electron. So very people would like to define, okay, the X-ray band is essentially the starts at the cutoff, photoelectric cutoff of the intergalactic hydrogen. Hydrogen ionization energy 30.6 electron volt. And the X-ray band, the X-ray photons have energies less than about 500 kilo electron volt. which is the electron proton and hydrogen magnets. So roughly speaking, this is the band, but there is no strict limit. When we say, as I said, it's from a fraction of kilo electron volt to all the way to 700 kilo electron volt. That's the typical X-ray band. And another point to note here is that in the entire electromagnetic band, the visible band is a tiny fraction. Okay, so while our X-rays are actually occupied quite wider band in the electromagnetic spectrum. So the information content is also regarding can be high in the X-ray band. How are X-rays produced? So as I mentioned, the X-rays are roughly 1,000 times more energetic than optical photons. Okay, this simply requires this X-ray production requires highly energetic particles or very high temperature. Okay, so if you want to see visible light, what kind of temperatures you need? Grow, for example, so about 10 power 4, 10 power 5 Kelvin, or you can use these discussed as well. You have if you know the temperature where the black body spectrum peaks, you can easily find out. So something like 10 power 4, 10 power 5 Kelvin, roughly about 10 power 5 Kelvin temperature is required to so that the visible the emission or the radiation peaks in the visible band. But for X-rays, it requires a million to 10 million degree Kelvin, much hotter compared to what we need for visible radiation. And not only the black body kind of thing, not only the thermal material with high temperatures, but highly energetic particles can also give rise to X-rays, and we will see some of these processes. Particularly in astrophysics, in the cosmic setting, X-rays are produced. I'm talking about the continuum X-ray radiation. The continuum X-ray radiation produced by three main processes. These are one of them is thermal Repson emission. The other one is the synchrotron emission and the impulse Compton emission. So these are the three main processes, and we'll go one by one very briefly. And then these are the continuum radiation, but there are also X-ray line emission. For example, in optical use, in the visible band, you see the Balmer lines due to hydrogen, for example. So similarly, in X-ray, of course, it must have energy. You also see the line emission, and line emission obviously is produced by transition in the atomic levels, particularly because the energies are higher. Though here the electronic transitions are from the inner atomic cells. When you have that, then you can produce X-ray lines. So let's go through one by one. The thermal Reynolds emission. Have you come across this term earlier? What is it? Can anyone tell? Okay, so thermal. This is essentially thermal emission from hot gas. So when there is a hot gas, essentially you have free electrons and ions. And when these free electrons are moving into the medium, into this kind of a hot medium, then they are interacting with the ions. And because of the Coulomb forces, they get decelerated. And you know in electrodynamics, if you have studied if there is a change in the speed, then there is a deceleration or acceleration. Accelerated charges increase. So in this process, the interaction between electrons and ions, because of the Coulomb interaction, the electrons they get decelerated, and that something like this electron passing through a photon changes its direction and speed. So this kind of because of this deceleration of these electrons, there is a radiation in the X-ray band, and we are talking about thermal plasma at a very high temperature, million to 10 million degree kind of temperature. So this kind of radiation is called thermal Bremsstrahlung emission. So essentially, due to the deceleration of electrons near the ions, that is the process which is giving rise to thermal Bremsstrahlung emission. How does it look like? If you have a thermal plasma at the temperature T, then the radiation spectrum, the intensity is a function of energy and a function of temperature, looks like something like this. So first of all, there is a continuum emission, and there are lots of the emission lines. The continuum radiation is because of this the loss of energy of the electrons, its motion. But then there are this lots of emission lines. So what is happening, because these ions are not fully ionized. So they have their electrons. All the electrons have been lost in the high temperature, but there are a few electrons attached to it. So what can this electron do? Electron can interact with such ion, and the electron can be recombined. Electron can get recombined with the ions, and that can produce downward transitions, and therefore the line emission because of the transition between atomic levels, and some of those lines are observed. In fact, a huge number of lines are observed in the thermal Bremsstrahlung emission. And in fact, you find such examples in astrophysics. If you have come across hot gas in astrophysics, clusters of galaxies, for example, the medium between galaxies in a cluster of galaxies is very hot, and that gives rise to this kind of thermal Bremsstrahlung emission because the temperature of the gas is about million or more than billion degree Kelvin. The other process, of course, is synchrotron emission. I'm sure you are aware of synchrotron emission, and synchrotron emission can come in radio, infrared, optical, ultraviolet, etc. And it can also come on X-ray. The difference here is that when you have X-ray synchrotron emission, you have really very the highly relativistic electrons. When highly relativistic electrons are moving in magnetic field, again there is a change in the direction, and that produces the radiation or the emission, which is called the synchrotron emission. And if you consider just one relativistic electron moving in a magnetic field, and if you observe the spectrum, it looks like something like this. So depending on the energy or the Lorentz factor of the electron moving in the magnetic field, the radiation actually peaks at certain frequency mu0, and this mu0 is even is related with this Lorentz factor square, something like this. And mu-z there is a gyro frequency. Okay, and if you have, of course, lots of this is just from the one electron, and there will be lots of electrons, and if because we are talking about very highly relativistic electrons, so these are not really thermal plasma, but so-called non-thermal plasma, where the energy distribution of electrons is like a power law. For example, the number of electrons at energy E is proportional to the energy to the power minus P, where P is the index for the power law energy distribution. If this were a thermal plasma, then what would be the distribution? Maxwell Boltzmann distribution. It is non-thermal, that is why it is a power law distribution. And of course, for one electron, it is like this. If the electron energies are distributed in the power law form, then from each of these electrons, you will get this one electron spectrum like this. And then in the total spectrum, you'll have to sum over all these individual electrons, like a spectrum, and the sum then looks like a power law. A power law distribution of electrons, highly relativistic electrons, generates the power law radiation spectrum. Here you see this is the flux as a function of the frequency, and this is in log plot. So power law just looks like a linear line in circle. Okay. So the things to remember is that a power law distribution of relativistic electron produces a power law form of radiation spectrum. And this power law has again index. So here it will be due to the power alpha. And then there is a relationship between the index of the spectrum alpha and the index of the energy distribution, power energy. And that relation is essentially alpha minus P minus 1/2. In fact, by measuring the spectrum, by observing with a telescope, let's say, the synchrotron spectrum, even in radio or other wavelengths, and if we have a power law spectrum, we measure that index, and then we can say something about the energy distribution of these particles. And when we have the energy distribution of particles, and also depending on this observed frequency, we can also find out what are the energies of this particle. And in general, particularly in X-rays and even in other, when the energies of these electrons turn out to be very high, then we ask this question: how do these electrons gain so much high energy? Then one has to talk about acceleration processes, which we are not going to do here. But that's how you progress from very simple observations. You measure the spectrum of the source. From that, you infer the particle energy distribution and the energies of the particles, and then you worry about how does these particles get so much energy. Then what is the processes occurring to so that these particles attain such high energies. These are really important astrophysical questions and different kinds of objects in high energy astrophysics. Another very important process in the high energy astrophysics is the inverse constant scattering. And what happens? And first of all, you know this constant scattering and inverse constant scattering. So when a low energy photon interacts with the relativistic electrons, then this low energy photon is essentially converted into high energy photon in the X-ray band, of course, depending on the energy of the electron. Okay, so if you have a gas or a medium of highly energetic electrons, even in thermal plasma with something like 9 Kelvin or so, and then you irradiate such a plasma with low energy photons like infrared, radio, optical, etc. And then you think about the interaction between these low energy photons and the high energy electrons. So then you get a spectrum which we call the interaction is of course with the inverse constant scattering, and depending on the energy of the energy of the photons and electrons, there can come from scattering as well as inverse constant scattering. But this process we call as quantization. Okay. And the result of quantization, what happens? So you have a plasma with a temperature KTE, let's say. TE is the temperature of the electrons. And these electrons are interacting with, let's say, a black body kind of structure with at a low energy. So, I mean, let's say the optical photons in the form of black body. So what happens in one scattering fraction, and then another important parameter is this optical depth that determines the scattering. Okay, so then in such a situation, you take a fraction tau, which is the optical depth of this black body spectrum, and because this optical depth is lower than 1, otherwise you will not get the power, the kind of spectrum we expect from inverse constant scattering or quantization. So you take a fraction tau of this initial black body spectrum, and that becomes that reduces in itself, so it comes down to. Then the black body spectrum is essentially upscattered to energies by this factor. So here KTE is the temperature of the plasma, where by emission square is smaller than the electrons. 1 plus this factor, that is the factor with which this energy of these black body photons are upscattered. So this you take this fraction and then move it here. So then this black body moves here in one scattering step. In another scattering step, again you take the fraction tau, again it comes down, then push it to higher energies because of this upscattering, and then every scattering step that keeps on happening. So this initial black body spectrum is moving towards higher and higher energy with the number of scattering increases. Okay, and this continues until the energy of these photons is comparable to the temperature or the thermal energy of the electrons. Okay, after that there is no more increase in the energy of photons because of the inverse constant scattering, so therefore there is a break. So the signature of interaction between the low energy photons and hot or energetic electrons is a power law spectrum, something like this. Again, this is the flux is a function of frequency, but again in log scale. Okay. So again, this linear line is actually a power law, and at high energy there is a cutoff. And by measuring the cutoff, one can tell about the temperature of the plasma. So this is the basics about the inverse constant scattering or process what we call quantization. Okay, so that's the three major processes which generate the continuum X-ray radiation. But as I mentioned, in addition to that, there are this line emission, and of course in thermal plasma, I described how the huge number of emission lines produced in thermal plasma because of the interaction of the electrons and the ions. But there is another process to generate the line emission. So this is the fluorescence line emission. What happens here? If you have a photon of sufficiently high energy to knock out one of the inert electrons in an atom. You can think of this atom, maybe iron or silicon or whichever atom. So if the photon energy is larger than the K cell ionization energy, in that case, this photon will knock out this K cell electron, and then it will produce a vacuum. So this is now with an electron removed from this ion is in excited state. So it relaxes by making a transition. One of the L cell electrons then jumps to K cell electron. And because of this is a transition between two atomic levels between L and K cell, and that produces photons of this energy, which is the energy difference between these two levels. So therefore, the characteristic energy of these photons at that generates, because you have so many photons with the same energy, and therefore that comes as a line emission. This is the fluorescence light. So, yeah.
Wouldn't the photon be more likely to hit the outer shell of the?
No, because that would fit you in simple terms you think of the wavelength of this photon and the size of the switch. Okay, so otherwise it is not possible. So if you have too high energy compared to the energy required to move the electron, that process is not very efficient. Yes.
In the previous slide, how do you distinguish if the power law is due to synchrotron or inverse complement?
That's very good question. In case of inverse complement scattering, we have a high energy break.
But even in the synchrotron, the higher energy ones lose their energy faster and it becomes sharper.
Yeah. So it becomes sharper, but the shape of the break is different. And another characteristic is, you have to look into other contexts. For example, if you have polarization measurement, then you are completely true. Synchrotron emission has very high polarization. But if you do not have the polarization emission, then you have to worry about whether there is enough magnetic field in that source, whether it can produce you have to use different kind of arguments. And even let's say in here, you can easily go to several hundred kiloelectron volt in terms of energy of the photons. In synchrotron, that is not always possible. It is possible, but not always, because to produce a synchrotron photon of a few hundred kiloelectron volt, the energy of the electrons required becomes very high. Then your acceleration process needs to be very, very efficient to produce that kind of highly energetic electrons, which is not easily possible. And then there are other things. For example, if you have this kind of inverse complement scattering, then you can also use information about this initial, what we call seed photon, spectrum of the seed photons. Whether this kind of spectrum, because obviously the spectrum depends on what is the spectrum of the low energy photons which you are illuminating. If that is varying, this will also vary. So, like that, there are various ways to distinguish. Initially, if you observe a power law, then it's a guesswork. But then you investigate more with additional observations and then find out what process is giving rise to whatever power law is you are observing. Okay, so this is about the fluorescence line emission, and these kind of line emission is very important in astrophysics, particularly when you are studying accretion of matter around this around black holes or neutron stars or even white dwarfs. Because in such situations, you can actually produce the fluorescence lines. And iron is one of the most abundant element, and it also has high fluorescence yield. So the iron K alpha, so-called iron K alpha line, which is a fluorescence line, is strong enough to be observed from this accreting black holes. And the iron alpha line actually actually arises from very close to the black hole. So therefore, its shape is affected by both by special and general relativistic effects. And this actually gives a way to throw strong gravity in accreting objects, and therefore this kind of observations, this kind of findings are very important in astrophysics. Okay, so That's about the processes that generate X-ray radiation, both the continuum radiation and as well as the line radiation. But how do the X-rays interact with matter? You already know this X-rays can knock out the electrons through this photolytic absorption. So if you have a slate of some material, something like this, with a thickness, let's say x, and then you illuminate X-rays with an intensity I0, and just across this slate, you try to observe how many are there, what is the intensity left after this X-rays pass through this conductor. So it is not the same. It is about I0 e to the power minus mu x. First thing to note is that there is no gradual loss of photon energy. I mean, it's not like, okay, this X-ray with a 10 kilo electron volt is passing through this, and then it reduced to some 1 kilo electron volt or some 5 electron volt. I mean, this is, that can happen in quantum spectrum. But this is, with the photolytic absorption, that is either the photon is absorbed or it passes. That depends on the absorption cross-section, of course. So the intensity of X-ray after passing through this slave of thickness X is essentially, if it is I0 is incidentally, then this I0 e to the power minus mu x, this this is the intensity left over. And the mu here is the diffusion coefficient that you can relate with the absorption cross-section and the column density like this. So the product of these two things, absorption cross-section into the column density, that is essentially the optical depth. So if you have intensity I0 incident, then I0 is equal minus tau, but tau is the optical depth. That is the intensity left over. And of course, this the interaction is to the photoelectric absorption, and if the X-rays are below about 50 kiloelectron volt. So in this case, of course, the X-rays will knock out one of the electron, and that electron which is ejected will have an energy which is the initial photon energy minus the binding energy of whichever cell we are considering. If it is a high energy, then it will be K cell. If the photon energy is less than the K cell energy, then it will be L cell and M cell like that. Okay, and this cross section, which essentially tells the probability of this whether a photon will absorb or not through this photon absorption process, that is function of the atomic number of this material in this slab, as well as the energy of the photons. So it is very something like number power cube and energy to the power minus 3. And this relation is correct above this edges. These are the ionization energy. This is for example, this is for silicon. This is the K cell ionization energy, and this is and then this is the above that K cell energy. So this you will see from here e to the power minus 3. This absorption cross-section simply decreases e to the power minus 3 above this K cell ionization. Okay, so you clearly see here that if the photons have energy is very just above this ionization energy, then our probability of absorption is very high to the photolytic cross-section. While if the photon energies are very high, something like 100 kiloelectron volt, 200 kiloelectron volt, this photolytic absorption process is not efficient in absorbing, because this absorption cross-section has become almost negligible. Okay, so that's about how X-rays are produced, as well as how X-rays interact, particularly the low energy X-rays below about electron volt interact with the material. So then the next question we are asked to ask is, what is X-ray astronomy, and then where are these X-ray observatories? Of course, when we talk about X-ray astronomy, we have to talk about observatories or telescopes. So, and what is the difference between X-ray astronomy and medical X-rays? For example, you may have seen X-ray images in doctor's office, and what type of detector telescopes are used in X-ray astronomy. So, some of these things we will let's go through. So when we say X-ray astronomy, essentially it is the study. I mean, this X-ray astronomy is essentially the study of X-ray sources that come from cosmic sources. Okay, for example, our own sun, X-ray binaries. You know what are X-ray binaries? Yes or no? So you know binary system of solar system. So these are essentially binary systems, but one of the components is a compact object, either a white dwarf or a neutron star or a black. In such situations, if the situation is favorable, then there is an accretion of material from the normal star onto the compact object, neutron star or black hole. And this accretion process can give rise to X-ray radiation, and that is why we call them X-ray binaries. Supernova and supernova remnant, active galaxies, galaxy clusters, which I was mentioning earlier. These are all X-ray sources, and the study of these sources is part of X-ray astronomy. Here, one example of the X-ray image of this galaxy in DC 4697. This is a Eastern galaxy, and it's a very different. The morphology of X-ray emission is very different from what you see in the visible light. Because in the visible light, it's elliptical. That is why it's classified as a. But here, first of all, we see these bright sources like the stuff. Most of these are these X-ray binaries, where either neutron star, black hole, or white dwarf they are taking material from the compact star. In addition, there are this blue region which is the diffuse emission. These are not point-like sources, but these are diffuse emission. And diffuse emission, how does the diffuse emission arises? For example, if we give them the multimedia gas, hot gas, which is producing this X-ray radiation through the thermal Ramaswamy process. So this kind of galaxies have this hot gas as well as this X-ray binaries here. Okay, so this is one example, of course. So where are these X-ray observations? So as I mentioned when we discussed how do the X-rays interact with matter, so the X-rays get absorbed. And our atmosphere has various elements, carbon, oxygen, nitrogen, molecules, etc. So these elements are the molecules, these elements in these molecules, oxygen molecules, or nitrogen molecules actually absorb X-rays. And therefore the X-rays cannot reach to the surface of Earth. So X-ray telescopes cannot be like ground-based telescopes. So if we want to do X-ray astronomy, then we have to put our telescopes and observatories above Earth's atmosphere. This particular part actually shows the transmission in the atmosphere, and from here you see there are few wave bands where the radiation actually can reach to the ground level. Visible band, of course, is one of this. But if you look at the ultraviolet, for example, it only reaches to about 200 kilometers. If you look at soft X-rays, again 100 to 200 kilometers. The harder X-rays penetrate very deeper, but again don't reach to the surface of the Earth. So that is why we need to send our observatories or the telescopes above Earth's atmosphere. If you want to do soft X-ray astronomy, it's several hundred kilometer altitude. While harder X-rays, which can reach up to about 25 kilometers or so, then hard X-ray astronomy can also be done with balloon-borne experiment. You fly your balloons at 30 kilometers, 40 kilometers high, then some of the X-rays can do that. And people actually have done, even in India, Tata Institute of Fundamental Research in Mumbai has actually a balloon flight or balloon-based hard X-ray astronomy. Longer people don't use that, but in Hyderabad there was a balloon flight center where they used to fly their hard X-ray detectors in balloons, and they would do this balloon-borne hard X-ray astronomy. But these days, satellite-based astronomy is much more common. So our X-ray astronomy is essentially done by sending telescopes in an orbiting satellite. Okay, so what this means is that first of all, this is very costly stuff. You cannot say these are not cheap, and the X-ray detectors have to work right the first time. If it doesn't work, if it fails, your hard work is done. So one has to prepare. One has to make the instruments very reliable. The components you use in this instrument, including detectors or other components in the integrated circuits, etc., semiconductor etc., have to be space qualified. Because in space there is lots of charged particles due to solar flare or due to other effects. So these charged particles will interact with the detector, telescope, etc. And if you are not using space qualified material, these things can get easily damaged, even if it works for sometime in the very beginning of the sending, but it will not last long enough. So these are very, very crucial. And because X-ray sonography is very expensive, there are not many X-ray observations like the number of ground-based telescopes we have. So these are some of the X-ray observatories that are currently operating. First of all, the Chandra X-ray observatory named after Indian American Nobel laureate Chandrasekhar was launched in 1990. It's still operating and producing excellent science. And you have already seen images, X-ray images from Chandra Observatory. It has fantastic spatial or angular resolution. So it produces very good X-ray images. Then we have XML Beacon. This one was the NASA satellite. This one is the ISSAA satellite, the European Space Agency satellite, XML Beacon. This one doesn't have that much angular resolution or that high angular resolution, but it's a collecting area is large, which means you are collecting many more photons. So you can do much better spectroscopy or timing studies. We will see. Then there is a SWIFT satellite again by NASA, and it is mainly for the transient objects. In the high-energy astrophysics, transient objects are very important. Things which are changing their state forever, or they are having very high flux for a short duration, or variable objects, etc. So then we have the NISTAR telescope. This is the hard X-ray telescope, hard X-ray focusing telescope. It is sensitive to hard X-rays. This is also producing excellent result. Then we have our own satellite, Indian satellite AstroSat, which was launched in 2015. It's still operating, and most of the launch instruments are still working. Then a newer one is the IUCAA. This is a German-Russian satellite which was launched in July 2019. And this is a survey telescope. It's surveying the entire sky in the X-ray band. I think from about a few electron, a few kilo electron volt all the way to electron volt. So it's discovering a huge number of sources. Unfortunately, due to the war, because this is a satellite between Germany and Russia, due to the war, there were issues, and this satellite was not being used for observation. It was kind of stalled for a long time. Okay, so some of you may ask, what's the difference between X-ray astronomy and medical X-ray imaging, for example? So in medical X-ray imaging, in doctor's office, so what you see, what you have is actually an X-ray generator, an X-ray source, which is generating X-rays. Then there is an X-ray camera, something like a film camera or something. So these days, even semiconductor detectors are used. In Pune, there is a company, just forgetting the name. They actually make this X-ray imaging machines, and they actually export to a lot of other countries. So then the distance between these two is few meters. Then if you want any body part to be imaged in X-rays, then like the hand, you put your hand between the X-ray source and the camera, and then X-rays pass through the body part and here. And as I mentioned, if the body part has heavy elements, then that will stop X-rays, and that will produce the dark regions here. And wherever this X-rays actually pass through very easily, then such dark regions will not be there. And therefore, if there is any defect in the bone, for example, as I mentioned, bone has calcium with a somewhat higher atomic number, that stops lots of X-rays. So if there is a defect in the bone, that will come out in this kind of image. Unlike in doctor's office, in X-ray astronomy, the sources are very, very far away. So in our galaxy, stars are extragalactic objects, and these sources are producing X-ray radiation. And we already mentioned some of the radiation processes, which is gamma or endoscopinization, or synchrotron radiation, for example. So through those processes, the cosmic X-ray sources are producing X-rays, and these X-rays are traveling through space. They travel through the intergalactic medium, if they are extragalactic objects, and the interstellar medium in our own galaxy. And then finally, they reach to the telescope, which is above Earth's atmosphere. And this telescope may have a collector or a optics, which essentially collects X-rays and then images onto a detector, that detector provides us with information about the X-rays which is emitted by this object. And what kind of detectors are, what kind of telescopes, what kind of detectors, what kind of information content is there? That is what I'm going to tell you. And when we're talking about low energy X-rays below about 50, 70 K kilo electron volt, then the infraction process is photoelectric absorption. So then one can very simply design a detector, which is the proportional counter, essentially a gas-filled chamber here, and an anode wire where you are applying high voltage. And then this is a container, and then there has to be a window made of some material which is almost transparent to X-rays. So the X-rays pass through this window and then interact with the gas here. And the gas field is usually one of the inert gas. And in this case, one can have xenon, for example, or organ, for example. Okay. So then what happens again? The X-rays interacts with this xenon atoms here, knocks out the electrons, and those electrons, wherever they are produced, because of this X-rays interact with this xenon gas, these electrons are accelerated towards the anode one because of the electric field, high electric field generated due to this high voltage. So when they are accelerated, they are gaining energy. And they gain enough energy very quickly to knock out electrons from other xenon atoms. And this process continues. So one photon initially generates one electron, but this electron, when it is accelerated towards this anode wire, generates a huge number of other electrons, secondary electrons. And those electrons are, of course, collected in the anode wire and the form of signal, and finally these X-rays are detected. So that is the basic principle of X-ray proportional counter used in the X-ray detector. And the proportional counters have been thrown in various X-ray missions, X-ray satellites. So this is called the Rossi X-ray Timing Explorer. This was launched and operated by NASA, and it worked from 1995 to 2012. Still, there are very useful data in the archive available, and this produced fantastic results, particularly because this kind of detectors can have very high time results of the order of microsecond. One can therefore study fast, rapid variability using such detectors. So this is one example of the X-ray proportional counter. First of all, the bottom part is actually the X-ray detector, and these small circles are all anode wires. So therefore, there are different layers of anode wire, and the X-rays come from this direction. And this particular structure is the collimator. So what is collimator? Collimator essentially collimates this X-ray, so it essentially limits the region of the sky through which this X-rays actually come and detect the detector. X-rays, if they are coming from far away from the pointing direction, those X-rays cannot reach to the detector volume. That is the role of this collimator. And one kind of collimator, honeycomb collimator, works like this. These are the metal plates kind of thing. So then if there are X-rays falling in such a way, so then only within this field of view, this X-rays can reach to the detector. If the X-rays are coming like this, they are absorbed by this plates, which constitute these collimators. So that is how you are, when you want to observe a source, then using these collimators, then you are observing that particular source, but not other objects. But again, depending on this height of this collimators, your field of view will not be too small. Sometimes you can have multiple sources, but the really bright sources are not very, very large in number, and then really these things are good to observe or isolate sources, are really good to observe sources. These are called proportional counter units. There was 5 such proportional counter units in this particular satellite's RXT. associate mission, the Indian associate mission also have this propulsion counter. This is called the large area X-ray propulsion counter because it has large area. There are three units and the total area about 6,000 centimeter square. So here only the detector part is on the collimator part. On top of this detector, there is also a collimator, just like what we saw in the RXPE vision. So the X-ray photons pass through this collimator and then finally go through this window and then interact in the gas. And when the electrons or the signal generated is measured by one of these wires. So this particular has sensitivity in the broad energy band, keeping it 80 kiloelectron volt. And again, it's a fantastic timing instrument for variability, fast variability studies. This is one of the best instruments. In fact, now at the moment, this is the best instrument for timing studies. Okay, so that's about the detectors I mentioned to you. These are kind of open without an optics, without a collecting area. You have a large detector like this, and then you are putting a collimator, and then you are limiting the sky, and then those photons that come from that part of the sky are inflected to the detector. This is not very not very efficient, not very ideal way to do. The best way to get a high signal to noise, which means you generate large number of photons with minimizing noise, is to use X-ray optics. And there are certain advantages. First of all, the X-ray optics one can use for collecting the things. You can have a large telescope and collect large number of photons, and then focus onto a detector. So and that means because your collecting area is large, you are detecting many more photons. Okay. Then that obviously results in a large collecting area, and then a concentrator. Once you are collecting these photons, then you focus onto a detector, which is essentially concentrated thing. And smaller the detector, your noise level is small. The detector is large, your noise level is high. So that way you reduce the noise level, and also of course you can image. When you are using optics, then you can image, and therefore you can distinguish different sources. In a given field of view, you can have hundreds of sources, but if you have fantastic resolution, fantastic imaging quality like the Chandra X-ray telescope has, you can study individual sources, and you can simultaneously measure background as well, because the high energy background is also variable. If you are not measuring the background simultaneously, there can be a lot of uncertainties. So these are some of the advantages of the X-ray optics. And of course, when you have image, then you have a morphology of the image. For example, that elliptical galaxy which I mentioned, that has certain distribution of the X-ray radiation within the galaxy. Then you can use your intuition to study the morphology and even to understand the physics of those sources. So, but making an X-ray telescope is extremely difficult. First of all, just like the mirrors used in visible radiation, if you use if you make X-ray optics or any kind of material and luminant X-rays through normal incidence, X-rays will not get reflected. X-rays will either pass through or get absorbed into the X-rays can be reflected only if they are incident onto materials or the optics or telescope through this grating angle. Grating angle is an angle between this X-rays which are incident and the surface of your mirrors. If this angle is very, very small, then only you can reflect X-rays. So it's a total external. The principle is essentially the same as the total external reflection. I'm sure you have studied total internal reflection when your reflection is internal to the medium. Here the reflection is out of the external to the medium. So this principle is essentially the total external reflection. And that works only if this grating angle, as I said, is very, very small. If it is high or if it becomes normal incidence kind of thing, X-rays cannot be reflected. So for very small grating angle, you see here the reflectivity is almost 100%. For example, below about 0.5 degree or so. And this angle, what we call is a critical angle, here that angle also depends on material properties. For example, the atomic number as well as the energy of the photons. So if this angle, if this grating angle is more than about 0.5, it effectively goes down very fast. Okay, so this kind of reflection is analogous to skipping the situation of skipping stone on a water where you throw a stone and then the water and then just touches the water and then flies like that. Okay, so this is how you can reflect X-rays. So then when you make X-ray telescope, then you have to take into account this kind of principle, this kind of requirement. Okay, and that results in the X-ray telescope optics, something like this. You have to use two kinds of mirrors. One is the parabolite mirror like this, and then another mirror which is hyperbolite. And when you have combination of the such mirror, for example, from here to here, one and another mirror which is hyperbolite, something like this. Then the X-rays which are incident and such that their grating angle is small. So then they will get reflected first from this hyperbolite mirror, then they then incident to the other mirror there, which is okay, first in the parabolite, then in the hyperbolite, and then there is a second reflection, then finally the X-rays come to this focus point. And this is how one can actually make focus X-rays, and this is called Walter one type geometry. And here is the Chandra X-ray telescope. So there are these four sets of this mirror pairs. This one, they say this is a parabolite and hyperbolite pairs, and then there are such four cells, the four set 1, 2, 3, 4. There are four rings like a cell, like this. And then the X-rays are called, which in this direction, then finally focus onto the detector. So this is how the X-ray telescope, Chandra X-ray telescope, and for the highest imaging quality, what you really need is a perfect hyperbolite and perfect parabolite shape. That is one requirement. The other thing is that the smoothness of the surface. So in this mirror surface is you see the wavelength of X-rays are few angstrom. I mean, they mention how much 1 angstrom to 100 angstrom. So if the surface is not smooth, if there is a roughness in the surface, which then the X-rays cannot be reflected, but the X-rays get scattered because of the roughness in different directions. So your reflectivity goes down. Your imaging quality is compromised. So unless you have a surface roughness of about let's say few angstrom level, you can have surface roughness at scales of few angstrom. Then so that you can focus reflect X-rays. If your roughness is stronger than that, or larger than that, will not be able to reflect X-rays effectively. Okay, then one counters, but the other kind of more workhorses these days are the CCDs, charge coupled devices. I'm sure most of you know this charge coupled devices. These are the semiconductor detectors, which are pixelated detectors. In one CCD detector, you can have millions of pixels. Your cell phones have something similar, kind of. There are CMOS detector, I think, and very similar to CCDs. So these are pixelated semiconductor detectors. Each pixel can have about 20 micron by 20 micron kind of size, and each pixel is a detector, so that the X-rays interact with individual pixels and get absorbed. That produces signal. That signal is stored in those pixels. Okay, for some for whatever you are indicating. Then those stored charges, generated charges are transferred from one pixel to another pixel by applying voltages. By varying the voltages, you can move the charges, and that is how you collect the charges and the signals generated by the interaction of X-ray photons onto the detector. And then this is a photograph of the detector. There are two kinds of X-ray cameras are the detector. So one is called the SSI, the points camera for imaging spectroscopy. These are used only for imaging sources. And then there are these S stand for spectroscopy, because there are gratings also, X-ray gratings in Chandra telescope. So these gratings are disperse light, the X-rays onto these detectors, and then you generate high resolution spectra. How much time? Yeah. So on Astro sector there is another telescope called soft X-ray telescope, which actually utilizes the X-ray optics. And here is the X-ray telescope. Here you will see there are roughly about 40 cells with inner, I think the inner diameter of 130 to outer diameter of 160 millimeter, and its focal length is about 2 meters. And there are again mirror pairs. These are not exactly paraboloid and hyperboloid. These are people actually approximate as a conical. People make a conic section so that it is easier to develop, easier to polish those things, etc. But then you compromise with the angular resolution of the telescope. So this X-ray telescope and even earlier telescopes like some of the Japanese telescopes, Asta, for example, or Suzaku, or these are the missions by Japan. Even maximum Newton doesn't have perfect hyperbolic. Only Chandra has very accurate parabolic and hyperbolic results, so that is why we get fantastic imaging quality. So the imaging quality is not great here in SFC. And again, but this telescope focuses on the detector. Again, this is a CCD detector, which is 600 by 600 pixels. The sizes of the pixels 40 micron. And there are some other details, technical details, which we cannot go, which we normally do say. So this CCD is read out every 2.37 seconds, and then whichever photons are detected in individual pixels, those are read out. Okay, and this telescope, even though it is not a fantastic imaging telescope, it's still useful because there are some of these telescopes which have excellent spatial resolution cannot really observe very bright sources because because of some problem called photon pileup. And when you are reading out these detectors, then your readout time is more than one photon interacts in a single pixel. Then the charges generated cannot be divided into two photons or something like that. So then you are incorrectly counting or also incorrectly measuring the amount of charges. And that situation happens for very bright sources. And that for very bright sources, when your image is very, very small in the detector, then there is obviously a high probability of one pixel having more than one photon interaction. While if you have a telescope which is not very large in collecting area and it is spreading the X-ray photons over the detector, then this possibility of this pileup reduces. And that is why it is the such telescopes are good bright sources. Okay, this is the X-ray CCD used in how the X-ray CCD works are the kind of geometry. These are called the frame transfer CCD. So this area is a sensitive area, detecting area, and there's lots of these pixels. So what happens every 2.37 seconds, these photons are interacting in these pixels, and after 2.37 seconds, the entire distribution of charges in different pixels is transferred into this so-called frame store region. Okay, and then this part of the detector is ready for observations. And in the frame store region, then by applying the voltages, then it is read out 2.37 seconds or whatever time you put. That is how this CCDs work, or either the mode is called frame transfer mode. Okay, so that's about. I told you about small number of telescopes or small number of types of telescopes and detectors. There are other kinds of detectors which we cannot cover in this first time scale. But these are the kind of workhorses are very regularly used kind of detectors and telescopes. So you have a fairly good idea about the X-ray detectors and telescopes used in various X-ray science. So now let's say you have an X-ray telescope which is operating level of Earth's atmosphere, and then you are looking at a source. And as I had mentioned, your X-ray source generates produces this X-ray radiation, this pass through the whatever medium is there between the telescope and source. If it is an extra galactic source, it will pass through the whatever IGM is there, then the X-rays will enter to our galaxies, pass through the ISM of our galaxy, and then finally reach to solar system and finally to the Earth above the Earth's atmosphere. So the X-rays can get modified with on the way, and that modification through X-ray photoelectric absorption, as you know. Okay, so then something is missing, some picture is missing here. Then this mirror, of course, will collect these photons and focus onto our detector. And before the detector, there can be a grating, like Chandra X-ray satellite or X1 Newton has grating. So this, if there is a grating, then the grating will disperse this light. And along the dispersion direction, there will be X-rays of different wavelengths of energy. Okay, if there is no grating, then these photons will directly image in the transportable devices, and those photons which interact with the detector, so that will generate an amount of charge, so that we can read out the amount of charge, and that amount of charge is a measure of the energy of the photons. Okay, and where is the location in the electricity detector? That location is essentially the direction of the photon through the system. Then the arrival time, one can also measure the arrival time at what exact time this photon interacted with the detector material. That is another kind of information. So these are the kind of information in the form of data. That is what we are getting. So as a result of observation of these X-ray sources, what we are getting some kind of a data. And the question for the astrophysicists or astronomers is that once we have this, as a result of this observation, we have data. So how to go from this data to the nature of the source or the astrophysics? That is the main question you want to ask, and you want to apply your physics knowledge or computational or whatever you want to do, and then finally try to understand what is going on, what are the physical processes going on in that source, what are the dynamical changes, etc. Then you study, and that is essentially the main theme of X-ray astronomy. So to do this, we need to understand the technicalities about the data, what kind of data, what kind of information is required, what kind of processing is done, what kind of the science data products are there. And you have some hands-on sessions which you will go through, and that is why also I am listing some of these things so that it becomes easier for you to grasp those things when you actually play with X-ray data. So first of all, X-ray detectors measure individual photons. So one individual photon is detected with the CCD pixel, for example, or a proportional counter. Then that one, when it is detected, when one individual photon is detected, then we call it an event, X-ray event. And the X-ray event essentially can have different attributes. One attribute is, as I mentioned, is the arrival time when it interacts with the detector material. Another attribute is the amount of charge, which is digitized in certain form called, then it is called pulse height amplitude. Essentially, the voltage, the digitized voltage. And after applying some corrections, the same thing is called PI, pulse invariant. I can describe later. Then, of course, the coordinates. This coordinates in the two-dimensional detector, of course, if there is just like a proportional count, no position sensitivity is there, then the proportional counter will not have that kind of position in the data, no coordinates in that case. And then attributes related to the quality of the event, because as I mentioned, these telescopes are operating in space, and there are lots of charge particles. Some of the charge particles can also generate these charges in the detector as a result of interaction between the charge particle and the detector. So which one is X-ray photon, which one is due to particles, etc. Some of these attributes will be there with some attributes saying that okay, this is an X-ray event, this is due to particle, this is background, etc. So those things will also be there. Some of the CCDs, because there are so many large number of pixels, so some of the pixels may not be good, may not be behaving well. So those will be called bad pixels, and the events will be bad events with those pixels. So those things will be there as well. And when you analyze your data, you throw out such bad data from bad events, etc. Okay, so these are the basic. So in astronomy, the data is essentially an event list. The file listing the various X-ray events. Okay, event number one. This was the arrival time at this time. This is the position X and Y coordinate in the detector. This is the pH value. This is the measure of energy. So like that, and then some event activities. So this list of events is essentially the main data, the main data file which you get from your observations, and that is what you people deal in the beginning. Okay. So this is an example of the event list. So there for one event there is various columns like this time. This is the arrival time. This is actually these are the coordinates in the different kind of coordinate systems. We can't bother right now with the so-called raw coordinate system, vector coordinate system, sky coordinate system. All these things are there. I mean, the one to give you a brief analysis, for example, one instrument can have several detectors. For example, several CCDs. Each of these CCDs will have its own coordinate system. That will be called the raw coordinate system. For example, raw X and raw Y is just that. Once you have a set of detectors, a two-dimensional array, then one can define a detector coordinate for the entire CCDs. So that would be called detector coordinate, detector X and Y. And then how these coordinates connect to the position in the sky. Those are called the sky coordinates. The sky X and Y essentially tell us about the coordinates of the source in the sky. So this is the difference. These are the different kinds of coordinates. And then the attributes like flag, pattern, etc. So you don't need to worry too much about that. But these are the kind of the attributes one event generally will have. And the data from one satellite to another satellite or one observatory from another observatory will vary. I mean, the conventions cannot be exactly the same. But the basic idea is this. Okay, so if you have a non-dispersive spectrometer like this, just the CCDs without a break. Okay, so in that case, what we have is the pulse height amplitude. This is a measure of the energy of the incident program. And when this thing is corrected for any special varies, for example, if you have a detector, one pixel may generate, for the sake, if your incident program energy is same, one pixel may generate certain amount of charge, another pixel may generate slightly different charge because of its response. In current, the detectors we have can only detect linear voltage. We have a new satellite called ISSAA-RCAA, launched by NASA. It's producing fantastic results. Probably you will see in some of the articles in Nature journal. And the current Nature journal in the cover page, there are this polarized images. You can actually check that. And currently, the X-ray detectors can only find linear polarization.
So, like, Chandra telescope has X-ray polarimeter on board.
Chandra accelerometer do not have polarization capability, so they can only measure the arrival time, the direction, or the energy of the photon. No
so, is it possible that it can be able to detect in future?
Not Chandra, but of course, as I mentioned, the another satellite called ISSAA, which was launched very recently and is producing fantastic results. So that was huge, very sufficient, but now we have X-ray. The name of the satellite is XPOSAT, X-ray polarization satellite, and it has one of the instruments called POLIX, which is again used to measure polarization, and it will be the IXPD, the NASA satellite for polarization is sensitive to soft X-ray polarization, but the one will be launched by India is medium energy. Okay, these are small satellite, and it will detect some sources, maybe sources, and once it is observed for long time still. But in future, India has plans to make much bigger polarization instrument, in all energies, soft X-rays, medium X-rays, as well as hard X-rays, and that is going to be one of the future. The physics, radiation processes involving X-ray polarization, the calculations, etc., are not easy, and some of you who join, then those are really challenging. I mean, making simulations, etc., for given type of force, geometry, etc. You can there is a lot of scope to work and produce very interesting results in X-ray polarization. Because that is a promise to do a lot of things, solve a number of things in various classes of objects. For example, currently there we do measure black hole spins or estimate black hole spins with different techniques. As I mentioned, one of the things is to use fluorescence lines, shape of the fluorescence lines to prove general relativity and even measure black hole speed. But the same thing can be done with, in other ways also. And there are controversies because people can do not agree many times. And X-ray polarization promise to measure black hole spin in a model independent way. There are many other things, many other promises this X-ray polarization has. Any other question? Okay, so anyway, you can ask me tomorrow. We have one more lecture on astronomy, and you have your hands-on session. So, Kavita, is it going to be here? Or okay. Huh?
It's from 4 p.m.
4 p.m. Yes. Okay, I'll